In this tutorial, we will see what one convolutional neuron can do. And as an example, we will see that using one convolutional filter, we can detect a square in an input image. Learning to detect a square using one convolutional filter. Overall, in this tutorial, we will see that we first create 1000 random images where 500 of them will have squares and the remaining 500 will not have squares in them. We will train one convolutional filter of size 5 by 5 to classify these two sets of images as having or not having square in them. And then we will investigate what the filter has learned and why the filter works, basically why the convolutional neural network works. And then we will also analyze correctly and incorrectly classified examples. So let's just start by importing the libraries that we need. We'll need NumPy and skimage to draw and matplotlib to visualize our input matrices and cbon also to visualize. Now first what I'm going to do is create 1000 images, each of size 10 by 10, having one channel each. So this is basically a 10 by 10 image, total 1000 of them. And I'm also going to create labels, the Y label. So this is my input X and this is my label Y, 1000 of them for each of these images out here. And we will initialize all of them to 0, but then we will make, for all the ones that have squares in them, we will make the corresponding ones 1. So for range 0 to 1000, for each image, skipping one at a time, that is all the ones for which we do not want to have squares are already done. So for the remaining 500, starting from 0, 0, 2, 4, 6, 8, and so on, we want to find a random location X in the 10 by 10 cell and random position Y. This gives me a random position in the 2D matrix. And then the random length is 1, so we want a square of size 3 by 3 such that, like, it's only one, a fixed size big. And then we draw a rectangle, and then we set for that rectangular region in the input image X to 1, so that we all have ones in the square positions. And then we also set the label of this to 1, so that we know that whenever we have a rectangle in the input image, we also set the correct label as 1. Otherwise, the label becomes 0. So for each input image out of the 1000, whenever we have rectangle in it, the output label is set to 1, and whenever we don't have a square in it, the output label is set to 0 by default. So let's run this as well. Now let's visualize how these inputs and corresponding outputs look like. So what I'm going to do is plot the first 16 inputs and the corresponding outputs. So I'm going to draw a heat map for all the inputs with the color intensities shown using blue, and also the labels in the title. So let me run this, and what we will see is the visualization of the input labels, input feature maps, and the corresponding labels. For example, in the first image, we have these random values, as you can see, and the corresponding label is a 0 because this does not have a square in it. Here's a second figure, second 10 by 10 random NumPy matrix. But here at a random position, we have a square in it, and the corresponding label is also 1. Again, the third picture, the corresponding label is 0 because we don't have a square in this. And here's a fourth image. We have a square at this random location, and then we have the corresponding label as 1. So here we can see that we have 16 images, 8 of which have squares in them, and the remaining 8 don't, right? And so let's see how many rows, how many columns we have in the dimensions of our input X and output Y. So input is 1000 images, 10 by 10 with only one channel, and output is 1000 rows, 1000 rows and single column because we only have the corresponding labels associated with them. Next, what we want to do is build a convolutional neural network model which takes as input one image, 10 by 10 by 1. Of course, that is number of images is controlled by the batch size, but it accepts an input of 10 by 10. And then we apply one convolutional filter. So this one indicates we are only using one filter. And the filter size we are going to use is 5 by 5. And then the output of this convolution, so if we apply a 5 by 5 convolution to a 10 by 10 input image, then the input dimensions shrink to 6 by 6. Because if you convolve a 5 by 5 filter on a 10 by 10 image, then each 5 pixels will average out to one value. So what comes out in this line number 6 is a 6 by 6 by 1 output feature map. And then we do something known as global max pool 2D. What this simply does is out of the 6 by 6 values, so out of the 6 by 6 matrix, which is equals to 36 values, it picks up the maximum value from the entire 36 values and then throws that as the output. So basically it checks for all the places if there is any square, and if the filter learns to detect a square, if this filter that we have, the single filter learns to detect a square, then out of these 36 values, at least one of them should have a very high value, and that's how the model can learn, the filter can know if there's a square or not. So let's run this. And then after this, we want to verify how our model looks, at least the number of parameters and so on, by using the model.summary. So here we can see that the input is 10 by 10 by 1. Conv2D gives us an output of 6 by 6 by 1. And the number of parameters associated with this filter is 25 plus 1, because we have a 5 by 5 filter. So 25 parameters plus 1 bias gives us 26 parameters. And then the sigmoid activation does nothing, and then global max pooling pulls out of these 36 values one maximum value. And this is the architecture of our network. Next, since this is a binary classification problem, we want to choose binary cross entropy as our loss. And we can choose any adaptive optimizer. And as a metric, we'll use accuracy. Our baseline accuracy clearly is 50%. So baseline accuracy is 50% because we have equal distribution of positive and negative labels. So now that we have done that, our model is already initialized to random values because we compiled the model already. Now we can see what currently the model's filter values, the weights in the filter look like. So what I'm going to do is model.getWeights, give me the weights of the first layer, and then the shape of the filter, and then I'm going to heat map plot the weights by using red colors. So if I do this, we can see that this is a 5 by 5 filter. I'm not plotting the bias, I'm ignoring that. Shouldn't matter much. And then I can see that the values are randomly distributed between, say, around minus 0.3 to plus 0.3. For example, this value here is 0.3, and maybe some of the values here, the white values are probably maybe minus 0.3 and so on. So our filter now initially is almost random, and it should not detect anything big because it hasn't learned anything yet. Now the next thing that I'm going to do is choosing batch size 10, which should not make a huge difference, but a reasonable batch size. Let me run for only 4 epochs of training with X as input and Y as the output. So we can see that the accuracy initially is around 50%, which is quite reasonable because the random baseline accuracy is 50%. If the model predicts everything to be a square, then it still will get 50% accuracy, right? But then over the 4 epochs, it actually learned something, and that's why the accuracy went up to 53%. So let me train further, maybe 16 more epochs, and see if the accuracy goes higher. So, okay, the accuracy actually went to 67%, so the model is actually learning even further, which is very good. Now let me train more 32 epochs and see if the accuracy goes even higher. Okay, we can see that the accuracy is going to around 75, 76. 76%, which is promising. So that means we are headed in the right direction. Let me train for 64 more epochs. And the accuracy is getting towards 80%, which is good. So the filter is learning. It's trying to see or understand what squares look like. Before we train any further, let's visualize the filter to see how the filter weights again look like. So I'm going to run this to see, okay, here's how our filter looks like. So filter has almost one values in this corner over here. It almost like a square. It has almost gotten the idea that if my input contains something like this, a square, then I should produce an output value of 1, which is pretty good. Ideally, we want this to be in the middle, but somehow the model learned that even having it at the corner gives a good accuracy. It is possible actually that the model may get stuck at a certain accuracy because the highest accuracy should be observed around when it's in the center. So the model is learning something. Ideally, we want all of these rectangular values, the values in the square, to be 1 and everything else to be almost a 0. So let's go back and train further, maybe 128 epochs this time, setting verbose equals 0. And again, I'm going to train it, actually verbose, setting verbose equals 1 to with number of epochs set to 256. Let's see if we get higher accuracy. So I can see that we already reached an accuracy of around 93%, sometimes jumping to 94%, which is quite good. So the model is learning to detect squares. It's not doing it perfectly, but I believe it's getting there. So 95%, we see that the accuracy is consistently around 95%. So the accuracy is around 96% at the end. So let me go back and train even further 256 more epochs to see if I can increase the accuracy further more than 96%. So we see that the accuracy settled down to around 96.8%, which is not bad. This is almost 100%, not exactly 100%, but almost 100%. So now let's go back and visualize the filter weights again to see how the values look like. Okay, this is actually surprising because for some reason it probably learned that a square could be here or it could be somewhere here and maybe even here, up here, or even down here. And somehow it seems it's actually overfitting. So it can detect squares, looks like, which is good, with an accuracy of 96, 97%. But I'm not getting the exact sort of pattern that I'm looking for. It is also possible that maybe the squares exists in various places in the picture, and maybe this is actually the correct way of identifying squares. But let me go back and even further train maybe 512 more epochs to see if my filter gets to the point where it can detect, like, squares by having the correct weights in the middle. So my accuracy has now gone up to 98%. Actually, it's getting even higher than 98. Okay, it's getting towards 99%. So after training for so long, it's almost 99% now. It is actually, yes, more than 99%, which is quite good. So the last stroke of these 512 epochs actually looks like helped the model learn what a correct rectangle is. Okay, so we're getting almost close to the final 512 epochs, and the accuracy we have is 99.6%. This is exciting. Okay, so now let's check for the filter weights again, and let's see how the filter weights look like. Okay, there we go. So this is slightly better. So it has now understood that it needs to focus towards the center of the filter. So if the center of the filter is almost ones all the way around, then it gets an accuracy of around 99.6%. I was thinking that if we maybe train even further, this line on the side should actually go away, and in the center there should be very light color as it is right now. So let's maybe even go back and train again. Well, actually, before doing that, let's go down and actually look at what the model takes as input and produces as output to analyze what the model is actually learning, what the filter has actually learned. So let's create another model with convolution filter 1, same as the original one, but this time the only thing that we don't have here is the global max pooling. So we create this model, I call this model intermediate, and then we save the model weights of the previous model to a.hdf5, and then I load the weights from the previous model, the pre-trained model, into my current intermediate model. So this intermediate model should give me a 6 by 6 output without actually doing the global max pooling. So I have the model, and then now what I'm going to do is in P, I'm going to keep the predictions of my from the original model, and in O, intermediate predictions. So let's obtain these predictions. Now next, let's check for examples that are misclassified. So what I'm going to do is for all the examples, I'm going to check if the prediction pi rounded value is equals to the correct label. So if the confidence is less than 0.5, then this round gives it a 0, and if 0 equals 0, then we'll continue. If not, we will go down and visualize the true versus prediction. So if you remember, when we went back, the accuracy was 99.6%, which means that out of the 1,000, there were how many examples? So out of the 1,000, 4 examples that were misclassified. So let's look at those. So this should give us those 4 examples, and let me run this to see if we get the same 4 examples. Okay, so we do have 4 examples. And the first one on the left here is, so the first plot that we have is y, which is actually the true label. And so here's y, and the true label is actually, this should actually be y, and then I should actually have here as yi, which is my true label. I'm plotting I'm plotting figure heat map xi. So this is my input feature here. So the blue one is my input feature, and here O is the output of the convolutional filter, because if you remember, we did intermediate prediction, intermediate model, and we kept the output to O. So basically what we have is here's our input in blue color. The picture on the right is the output from the convolutional filter, and here's the predicted confidence. So for this picture, we have a higher signal around this area, which is actually around this area. So it thinks that there is a square here on this region with a confidence of 0.56. So it almost got it wrong. I mean, it got it wrong, but very closely. So there is no square here. It looks like, probably it looks like there's a square, but there's no square. And it thinks it's a square with a confidence of 0.56. So wrong, but very close. Here's another one. So it thinks that actually there's a square in this region over here, maybe 5 by 5. So it thinks that probably there's a square over here, and that's why there's a high signal. And because of this, the confidence is only 0.5, so very close. If it was 0.49, this would be correct. Here's one example where it made quite big mistakes. So here, it probably thinks that there's a square here, which actually it looks like a square. I mean, this is actually an example where maybe randomly we had a square here, and it thinks it's a square. So this is actually, even though this is technically incorrect, the model actually did not do a bad job here, because this indeed looks like a square. Another example where it failed is this one. So it marginally failed here. There's no square on top region, but somehow it thinks that there's a square, maybe because of the pixels, these high pixels around this region. So these are incorrect examples. Now let's look at some of the correctly classified examples. Maybe let's look at 4 correctly classified examples. Well, maybe let's look at 10, and out of 10, we see how many of them are correctly classified. Okay, so now if we go back and look at the correctly classified, here's the input. So it doesn't have a square. It predicts a confidence of 0.0, which is correct. Here we have a square, and it does find that it's a square on the top region. So for some reason it didn't detect it in the center, but maybe it's the way the filter is designed. So this is correct too. Here we have a square here, and it thinks that a square is slightly below. So the way it detects a square is not absolutely correct, but it somehow has learned to detect squares. Let's actually, to investigate more, let's actually go back and train further 512 epochs to see if it learns to centralize this and see if that works. So let's go back and train more 512 epochs. So the accuracy that we already had is 99.6%, and let's see if we can get any further or higher accuracy than that. Oh, well, actually, yeah, it's 99.7% now, so it probably got some of the remaining examples correct, and sometimes it's jumping to 99.8%. So okay, so this is now consistently 99.8%. I will actually be surprised if it gets 100%, because if you remember this example here, actually, even though this is random numbers, this does look like a square. So I wouldn't be surprised if it gets considers that as a square. So 99.9% accuracy should be enough for us actually. Oh, it's actually getting 100% accuracy occasionally. It's already getting 99.9% accuracy and almost 100%. Okay, so it looks like it consistently is getting 100%. So it has already learned to classify everything probably very correctly. Okay, so once the 512 epochs are done, we will check if there are any missing examples. There probably won't be any, because once the accuracy is 100%, it correctly identifies all the examples. It will be interesting to visualize the filter and see how the filter looks like. So 512 epochs are done. We have 100% accuracy now, which is great. Let's see how the filter looks like. Okay, there we go. So now we have actually have a really good filter here with a clear sign that has almost very high values like 5 as a square in the center, and everything else is like a zeros in the outside. And this very clearly, this is the one that we were looking for. This filter actually detects squares in the input image of size 3 by 3. So then if I recreate another model and load the weights and do the predictions, if I check for misclassified examples, I'm getting none because everything is classified correctly. And let's see if we can look at the correctly classified examples, maybe some of them. So here, let's look at the first one. So here, this one, this is not a square, done correctly. Here, there's a square here, so it thinks that it's getting a higher value around this region, right? Because we have 2 pixels down. So if we remove, actually this is correct because 10 by 10 reduces to 6 by 6. So the center here is actually over here. So this actually exactly learned to find a square center and produce that as a very high value. So clearly, this is the power of a single convolutional filter. So one filter, when it learns to appropriately set its weight, so let's actually print these weight values to see how they look like. Filter weights, I can actually do print filter weights to also look at the values. Okay, so they actually have, I mean, these numbers are long floating point numbers. So let me see if I can wrap them and only print 2 decimal points in a single 2D matrix. Let's actually look at the shape of the filter dot shape to see what the shape looks like. So it's a 5 by 5 by, sorry, 5 by 5 by 1. So let me print shape filter weights, and then all rows, all columns, 0 here, 0 here. This gives me 5 by 5 filter. There we go. So here are the filter values. Almost zeros on the top row, almost close to 0 on the top first column, exactly high values here, high value here, high value here, and really high values here, and low values here. So it is actually a square. As you can see, the filter has formed itself to be a square. So now when this filter actually multiplies the input, whenever there's a square in the input, then we get a higher value. Otherwise, we get lower values. So overall, what we saw is the power of one single convolutional neuron. This is how convolutional neural networks operate.